Hello everyone, and welcome to week 3. This week, we're going to wrap up our discussion of the t-test and introduce a new type of statistical test, the ANOVA. We'll begin this video by discussing null hypothesis significance testing with regards to z-tests and t-tests. We'll then talk a little bit about the underlying assumptions of t-tests, and then move on to a discussion of dependent samples t-tests. Let's begin by talking about null hypothesis significance testing. We want to determine whether a given effect, for example, a difference between sample means that we observe, reflects a true effect, for example, a difference between population means, or whether it is merely due to chance, for example, sampling error. We can calculate standard error, which tells us the average variability that is expected due to chance. And based on standard error, we can calculate a test statistic, the standardized difference between our observation and what would be predicted by the null hypothesis. This test statistic represents a ratio of systematic variability to unsystematic variability. Importantly, we can model how test statistics should be distributed if the null is true, and this means that if our test statistic is sufficiently extreme, it is unlikely to occur if the null is true, and therefore we can reject the null. The alpha value that we pick determines what counts as sufficiently extreme or sufficiently unlikely. There are two types of errors that we can make here. A type 1 error occurs when we reject the null when there's actually no effect, and we can control our chance of a type 1 error by changing our alpha level. A type 2 error occurs when we fail to reject the null when there is an actual effect, and we can control our risk of type 2 errors by increasing our sample size and increasing the effect size of our manipulation. Let's take a minute to review the different types of tests that we've covered so far and what types of comparisons they make. First, we might compare a sample mean to a population mean. Here, we're asking, did this sample come from this population, the null population, or from an alternative population? We can use a z-test if the population standard deviation is known, or a one-sample t-test if it is unknown. If the sample mean is significantly different from the population mean, then it's unlikely that it came from the null population. And here, we would decide to reject the null hypothesis and conclude that the sample came from an alternative population. We can also compare two sample means to each other. This is useful when the population mean is unknown. Here, we're asking, did both samples come from the same population, or from two different populations? For this comparison, we use an independent samples t-test. If the sample means differ significantly, it is unlikely that the two samples came from the same population. Now, importantly, all of these tests have assumptions that must be met in order for the logic of null hypothesis significance testing to hold. In other words, for us to be confident about how likely a given test statistic is to occur if the null is true. Most of these assumptions are about the dependent variable, or dv. In other words, the variable that we're measuring. Let's talk about some of these assumptions now. The first assumption of the t-test is that the dependent variable is on an interval or ratio scale. So, to briefly review some content from Psych 10a, there are 4 levels of measurement that we deal with. Nominal measurement assigns names, from the Latin nomen, to categories. So, for example, if our variable is ethnicity, we could have categories for European American, African American, Asian American, so on and so forth. When we measure data at the ordinal level, we put our categories into order. So, for example, first, second, or third place. When we measure data at the interval level, we can be confident that the intervals between scores are equal. For example, IQ scores. And notice the distinction here between interval and ordinal data. We know for a fact that the difference between an IQ score of 101 and 102 is the same as the difference between an IQ score of 112 and 113. But for ordinal data, we have no way of saying if, for example, runners that came in first and second place in a race had the same difference in time as runners that came in second and third, or seventh and eighth. Finally, when we measure data at the ratio scale, we have a meaningful zero, which allows the calculation of ratios. This is the case, for example, with distance or counts. Not only do we know that the difference between 5 and 10 meters is the same as the difference between 25 and 30 meters, but we know that 10 meters is twice as far as 5 meters. For t-tests, the dependent variable must be measured on an interval or ratio scale. If the dependent variable is nominal or ordinal, we have to use a different test. The second assumption of the t-test is that the dependent variable is normally distributed. In other words, the distribution of the dependent variable in each sample should be approximately normal. Now, fortunately, because of the central limit theorem, this should be true by definition if our samples are sufficiently large, specifically if each sample size is greater than 30. Remember that with a large sample size, the sampling distribution will be normal, even if the population distribution is not. That being said, it's always worth checking through data visualization, in other words, histograms, how normally distributed your data actually is. If the dependent variable is severely non-normal, you may need to use another approach. Our third assumption actually applies only to independent samples t-tests, and this is the assumption that the variance of both populations is roughly equal. This is known as homogeneity of variance. We can express this mathematically like so. The variance of population 1, represented by sigma squared, is approximately equal to the variance of population 2, also represented by sigma squared. We can take an educated guess at whether or not both our populations have similar variance using a test called Levene's test. More generally, however, homogeneity of variance is not a concern if the samples are sufficiently large, if you have more than 100 participants per group, if the sample sizes are equal, and if the sample variances are roughly equal. In other words, as long as one sample variance is not more than twice as much as the other, you should be good to go. You can also avoid this problem entirely by conducting Welch's t-test, which does not assume homogeneity of variance. In this course, you will not need to calculate Welch's t-test by hand. However, conveniently, R does Welch's t-test by default. The fourth and final assumption of the t-test is that observations, in other words, data points, in each sample are independent. This means that observations should not predict each other, and, more practically, that any given individual should only be in one group. There are a couple of ways that this assumption can be violated. The most obvious is if you have multiple observations of one participant. If the same person is in both groups, that violates the independence of observations. This can also occur, for example, if you have two participants chatting with each other as they fill out their questionnaire. In this case, their responses to the questionnaire will probably resemble each other more closely than other participants would. The assumption of independence of observations is absolutely crucial to the t-test, and unfortunately, it's also not testable. The only way we can be sure that our observations are independent is through our experimental design. For example, ensuring that participants are only observed once, and that they are randomly assigned to groups. However, what about situations where we want to measure participants more than once? Let's talk a little bit about why we might want to do this. So, imagine that we want to study how ratings of attractiveness are influenced by information about a person's moral character. So in other words, if you see a photo of someone and are told that they volunteer at an animal shelter helping cute little puppies find their forever home, will you find them more attractive? On the flip side, if you're shown someone's photo and are then told that they have never once picked up after their dog, maybe you'll find them a little less attractive. So, for this study, let's say that we show participants photos of faces, present either positive or negative information about the person in the photo, and ask them to rate the person's physical attractiveness on a 1 to 10 scale. We then compare attractiveness ratings between positive and negative info conditions. Now, a problem we might run into here is that beauty is in the eye of the beholder. Different people define attractiveness in different ways. This means that responses will vary depending on each participant's definition, and that will introduce unsystematic variability to our data. There's also the issue of relationship status. People in relationships may be less likely to rate others as attractive, and people looking for relationships may be more likely to rate others as attractive. So here, differences in participants' relationship status may also introduce unsystematic variability to our data. So how might we reduce this unsystematic variability and thus increase our power? Both of these sources will cause variability between individuals, but not within individuals. So, for example, no matter what a participant's definition of attractiveness is, they're going to apply that same definition to every photo that they rate. And, by the same token, no matter what someone's relationship status is, that relationship status is going to affect their ratings in the same way, no matter how many ratings they give. So, we could ask participants to rate attractiveness twice, once on a photo coupled with positive info, and once on a photo coupled with negative info, and then compare attractiveness ratings within participants. This could help us to reduce unsystematic variability in our data. However, doing so would violate the assumption of the independence of observations, and this means that we cannot use an independent samples t-test. Instead, we need a new type of test. And, as you might have guessed from the title of this lecture, this is going to be the dependent samples t-test. A dependent samples t-test compares two samples, just like an independent samples t-test. However, in an independent samples t-test, the samples are independent, as you might have guessed from the name. Each participant falls into exactly one sample, and each participant is observed exactly once. In a dependent samples t-test, the samples are dependent. We have the exact same participants in both samples, and each participant is observed twice, once in each sample. Crucially, the dependent samples t-test does not assume the independence of observations. So, let's go back to our example study, examining attractiveness and moral character. Our research question is, does information about someone's moral character influence how attractive they're perceived as being? So we'll show each participant photos of two faces. We'll assume, for this example, that participants' ratings of attractiveness are not influenced by their gender or by the gender of the faces. Now, of course, this is almost certainly not true in real life, but for the purposes of this example, we'll assume that it is, because it makes things way simpler. We'll give positive information about one photo and negative information about the other. Now, the order in which we present these photos could in theory influence our results. For example, participants might always rate the second photo as being more or less attractive than the first, just because now they have something to compare it to. The solution is to counterbalance or randomize the order of presentation. In other words, some participants see the photo coupled with positive information first, while others see the photo coupled with negative information first. Counterbalancing and randomization actually increase unsystematic error, but importantly, they help us to avoid bias. Finally, we ask participants to rate each person's physical attractiveness on a 1 to 10 scale. So, now we have two groups, and thus two group means. In group 1, we have ratings of attractiveness for faces coupled with negative information. In group 2, we have ratings of attractiveness for faces with positive information. So, what is different about these two groups compared to the two samples we used for an independent samples t-test? And the answer is that here, both groups, or both conditions, consist of the exact same people. Dependent samples t-tests reduce unsystematic variability because they allow us to ignore differences in the dependent variable between individuals. For example, individual definitions of attractive or individual relationship status, and to focus on differences in the dependent variable within individuals between conditions. For example, the effect of moral character on ratings of attractiveness. Let's look at a graphical representation of our conditions. So here, our x-axis represents ratings of attractiveness, lower values on the left to higher values on the right. This blue curve represents the distribution of attractiveness ratings for faces that are paired with negative information. The curve represented by the dashed red line represents the distribution of attractiveness ratings for faces paired with positive information. And we can represent the mean of group 1 with the vertical blue line here, and the mean of group 2 with the vertical red line here. So, in general, we're interested in the difference between group 1, the faces paired with negative information, and group 2, the faces paired with positive information. But crucially, unlike an independent samples t-test, here we want to keep track of each individual's change across time. So, let's say that participant 1 gives a slightly above average rating of attractiveness for the face paired with negative information. We then want to see how they rate the face paired with positive information. And here we see that they rate the face paired with positive information much higher. We then look at participant 2, see what rating they give the face paired with negative information, and then see what rating they give the face paired with positive information. Finally, we do the same thing for participant 3, first for the face paired with negative information, and then for the face paired with positive information. So again, here we have 3 participants, each one measured twice, represented by the blue and the red, respectively. And what we need to find out are their individual difference scores. In other words, for each participant, what is the direction and the magnitude of the change between the faces paired with negative information and the faces paired with positive information? And that's what the length and direction of these gray arrows here is representing. Notice that for participant 1, we have a very strong change, such that the face paired with positive information is rated higher than the face paired with negative information. For participant 2, we have a change in the same direction, but it's not nearly as large. And for participant 3, we actually have a smaller change in the opposite direction. So, as I mentioned before, simply comparing sample means will not be sufficient. We need to track how each individual score changes between groups, in other words, between conditions. And the solution is to calculate difference scores for each individual. So, let's say we look at 4 of our individuals and calculate their ratings for group 1 and for group 2. We then can calculate the difference in their ratings simply by subtracting their rating for group 1 from their rating for group 2. So here we see that 3 out of our 4 participants have positive differences in rating, meaning that they rated faces in group 2, the faces paired with positive information, as more attractive than the faces in group 1, the faces paired with negative information. The one exception to this is our second participant, Maro, who rated the faces in group 1 slightly higher than the faces in group 2, and thus has a negative difference score. Difference scores, represented by x sub d, are treated like raw scores. Each participant has a single difference score, and these difference scores are used for our calculations. We no longer care about their actual responses in each condition. Our conceptual question here is this: is the mean of difference scores in the sample significantly different from the mean of difference scores expected by the null hypothesis? So here, the mean of difference scores in the sample is 2.85. The null, on the other hand, predicts a mean difference of 0. Some differences will be positive, some will be negative, but in the long run, they all cancel each other out. Now let's look at a graphical representation of null hypothesis significance testing for the dependent samples t-test. The blue curve here represents the distribution of mean difference scores if the null is true. And as I mentioned before, the population mean of mean difference scores under the null is 0. Now, let's say that the mean of difference scores from our sample falls here in the distribution. Our question is, how likely is the mean of difference scores that we observed to occur if the null is true? Let's begin, as always, with step 1 of null hypothesis significance testing, setting the null and alternative hypotheses. So again, our research question is, does information about someone's moral character influence how attractive they're perceived as being? Our null hypothesis will be that participants' ratings of a person's attractiveness will not differ depending on whether they receive positive or negative information about that person's moral character. We can represent this simply by stating that the null hypothesis is that mu sub d, the population mean of difference scores, is 0. In other words, there is no difference between the population mean for attractiveness in the positive info condition and the population mean for attractiveness in the negative info condition. Our alternative hypothesis will be that participants' ratings of a person's attractiveness will differ depending on whether they receive positive or negative information about that person's moral character. We represent the alternative hypothesis with mu sub d does not equal 0. In other words, there is a difference between the population mean for attractiveness in the positive info condition and the population mean for attractiveness in the negative info condition. Crucially, note that this is a two-tailed, non-directional hypothesis. We hypothesize that there will be a difference, but we do not hypothesize in which direction it will be. Now that we have our null and alternative hypothesis, it's time to determine alpha and from it our critical value. So, let's go with an alpha of 0.05 and, as I already discussed, a two-tailed test. Degrees of freedom for dependent samples t-tests is equal to n-1, just like for a one-sample t-test. And this is because we only have one mean, m sub d, the mean of difference scores. So in this case, If we assume that our sample size is 60, our degrees of freedom will be 59. And this is the case even though we actually have 120 data points, because each participant was measured twice. Remember, n is the number of participants, not the number of observations. We still use the table of critical t-values, just like we did for the one sample and independent samples t-tests, because this is still a t-test. Our critical value will be 2.021. As I mentioned before, always underestimate degrees of freedom if the precise degrees of freedom for your experiment is not shown in the table. Now that we have our alpha level and critical value, it's time to calculate the test statistic. The equation for the test statistic in a dependent samples t-test is shown on the right, and below it, the equation for the standard error used in the dependent samples t-test. The numerator of the t-test here is the mean of the sample's difference scores, m sub d, minus the mean of the population of different scores if the null were true, mu sub d. The denominator is the average difference, or variability, between the mean of a sample's difference scores and the mean of the population of different scores that would be expected if the null was true. And we find this value, in other words, the standard error, by dividing the standard deviation of different scores by the square root of the sample size. We have two groups, or conditions here. In group 1, we have attractiveness ratings of faces paired with negative info, while in group 2, we have attractiveness ratings of faces paired with positive info. We have no use for the descriptive statistics of each of these conditions individually. Rather, we're interested in how participants' ratings change between the two conditions. So, to calculate our test statistic, we first need to calculate difference scores for each individual. So here, we have a table in which each row represents one participant, and each column represents their responses to one of the two conditions. On the left-hand side, we have ratings for faces with positive info, group 2, and on the right-hand side, we have ratings for faces with negative info, group 1. Notice that this table is abbreviated. We're seeing the first 6 participants here, as well as the 60th participant. Obviously, the full table would be a little bit too big to fit on the slide. So, knowing the responses in each of the two conditions, we can calculate the difference rating, as we see in this column here on the right. And again, these are simply the differences between the positive info and negative info condition. Once we have all 60 difference scores, we can then compute the mean, m sub d, and standard deviation, s sub d, of these differences. So again, I'm really blowing through the math here. I strongly encourage you to watch Dr. Albada's stats class video on this topic. Also note that the mean and standard deviation that I report here are not just for the 7 data points shown on the slide. They're for our full data set of 60 participants. So now that we have our mean difference and the standard deviation of the mean difference, we can calculate our test statistic. We'll begin by calculating the standard error. The standard deviation of our differences, 0.95, divided by the square root of our sample size, 60, gives us a standard error of 0.12. We then plug this into the denominator of the equation for the test statistic. In the numerator of the test statistic, we subtract the hypothesized population mean difference, which is 0, from our observed mean difference in our sample, which was 0.62. Dividing 0.62 by 0.12 gives us a t-value of 5.17. Again, really flying through the math here, I strongly encourage you to watch the stats class video, which goes through this process in more detail. Finally, step 4 of null hypothesis significance testing is to make a decision. Our test statistic, 5.17, exceeds the critical value, 2.021, that we identified previously, and so we reject the null, and conclude that positive as opposed to negative information about a person's moral character increased participants' ratings of their attractiveness. Crucially, running a dependent samples as opposed to independent samples t-test reduces unsystematic variability from definitions of attractiveness, relationship status, and from anything else that might vary between participants. And this reduction of unsystematic variability increases the likelihood that we will be able to reject the null if the effect exists. In other words, it increases the power of our test. Effect size for dependent samples t-tests is calculated, once again, with Cohen's d. Here, Cohen's d measures the mean of different scores in standard deviation units, and is given by the formula m sub d divided by s sub d, or the mean of different scores divided by the standard deviation of the different scores. Here, our effect size calculation would be 0.62 divided by 0.95, which gives us a d of 0.65. Cohen's d is interpreted using the same rules of thumb that we did for Cohen's d in the context of the one-sample and independent samples t-tests. Cohen's d of 0.2 is considered small, 0.5 is considered medium, and 0.8 is considered large. So here, our effect would be considered medium to large. This tells us that providing positive, as opposed to negative, information about a person's moral character increased participants' ratings of their attractiveness by a moderate amount. We would report these results as follows. As with reporting results from a one-sample and independent samples t-test, there's a lot of specific information that we need to include here, but the way in which we include it is fairly formulaic and thus fairly straightforward. Let's walk through each of the components in turn. We begin by stating the type of test that we ran, a dependent samples t-test, stating whether it was one or two-tailed, here it was two-tailed, and stating the alpha level that we chose. We next provide a brief statement of our research question or hypothesis. Why did we run this particular test? We give a brief statement of the effect that we observed, here a difference in ratings of attractiveness, and then we report the result of the t-test itself. Just like for an independent samples t-test or one-sample t-test, we put the degrees of freedom inside the parentheses that follow the italicized t. We then report the test statistic itself, following the equal sign, and report our p-value. Here, we didn't calculate a specific p-value, but because our test statistic exceeded our critical value, we know that our p-value must be less than 0.05, following the same logic that we outlined in previous lectures. We include the mean and standard deviation of group 1, along with the mean and standard deviation of group 2. We present our effect size and give a brief verbal description. So not only does d equal 0.62, but we describe this effect size as medium to large. And we conclude by tying these results back into our research question. So here, providing positive as opposed to negative information about a person's moral character increased participants' ratings of their attractiveness. So, a quick reminder about rejecting the null hypothesis. We can reject the null hypothesis in two ways. Either when the test statistic exceeds the critical value, or when the p-value is lower than our alpha value. These two ways are always tied together. If the test statistic is greater than the critical value, then the p-value must be less than the alpha value, and vice versa. In general, for hand calculations, it's much easier to compare the test statistic to a critical value we've identified ahead of time. When using R, however, you will simply compare the p-value that R gives you to the alpha level that you selected. Let's talk a little bit more about power in dependent samples t-tests. As we've mentioned before, dependent samples t-tests can increase power by reducing unsystematic variability. This increase in power is proportional to the correlation between participants' scores in each condition. Now, we'll be talking about correlation in much more detail in a week or two. But for now, just know that when we talk about correlation, we basically mean, for example, do participants who have above average scores in condition A also have above average scores in condition B, even though the means of each condition are different? The smaller this correlation is, the less power you gain from doing a dependent samples t-test. So let's talk about this idea in a little bit more detail. So here, this vertical blue bar represents the mean of condition 1, and this vertical red bar represents the mean of condition 2. So let's say the participant 1 gave the following responses in condition 1, represented by the blue p sub 1, and in condition 2, represented by the red p sub 1. So notice that in both cases, this participant was above average for their respective condition. Here, same idea. Participant 2's responses were slightly below the average in each condition, and participant 3's responses were a little bit more below the average in each condition. So this would be an example of a situation where we have a high correlation between participants' scores. If a participant is above average in one condition, they're likely to be above average in the other condition. If they're below average in one condition, they're likely to be below average in the other condition. Now let's consider a circumstance where participant 1's responses look like this. They are above average in condition 2, but below average in condition 1. Participant 2 is about average in condition 2, but above average for condition 1. And participant 3 is way above average for condition 1 and below average for condition 2, so much that the scores actually cross over. This would be an example of a situation where we have small correlation. Here, the increase in power that we would get by running a dependent samples t-test would be much smaller. One other thing to note here is that a dependent samples t-test requires half the number of participants compared to an independent samples t-test, which is awesome. Participants are hard to come by, and it takes time and money to get people to participate in our studies. However, cutting the sample size in half also cuts our degrees of freedom in half, which increases our critical value. This is less good. Now, importantly, as long as participant scores are moderately correlated, the power that we lose by reducing our degrees of freedom will be made up for, and then some, by the reduction in unsystematic variability. The only exception would be if participant scores in each condition were more or less uncorrelated. And if that's the case, it kind of leads us to question whether our samples are actually dependent at all. The big picture here is that as long as your samples are somewhat correlated, which they should be if they're dependent, you will always gain more power from your reduction in unsystematic variability than you will lose from your reduction in degrees of freedom. I want to wrap up this lecture by clarifying some terminology. The first term we'll talk about are within subjects or repeated measures designs. This refers to any experimental design in which the same participants get measured or observed in more than one condition. Dependent samples t-tests analyze data from repeated measures designs that have exactly two conditions. If we have more than two conditions, we'll need to use a different type of test, which we'll be discussing in the weeks to come. The terms paired samples t-test or repeated measures t-test are other names for the dependent samples t-test. A matched pairs or matched subjects design is a special type of experimental design in which pairs of measures are from two different subjects that have been matched on some criteria. For example, let's say we wanted to investigate the effect of tutoring on students' GPA. We could match participants based on their current GPA to minimize unsystematic variance in outcomes due to differences in GPA. We could then test our hypothesis via a dependent measures t-test. A couple other things to keep in mind when using repeated measures designs, including dependent samples t-tests. In general, repeated measures designs, like the dependent samples t-test, are very useful. As I mentioned before, you only need half as many participants, and they can substantially reduce unsystematic variability and thus increase power. However, some independent variables can't be manipulated within subjects. For example, if we want to study the effect of things like participants' gender, participants' ethnicity, participants' political ideology, or participants' personality, there's no way to manipulate that within a participant. It has to be done between participants. We can also run into what are known as carryover effects. This occurs when the effects of one condition carry over to the other. For example, let's say that we wanted to explore the effect of emotional states on some particular dependent variable. We might have participants watch a movie clip designed to make them feel happy, then fill out a survey, then watch another video clip designed to make them feel sad and fill out another survey. The problem is, there's no guarantee that they'll be done feeling happy from the first movie by the time they fill out the second survey. And in this way, the effect of the first condition will carry over to the other. We can also run into what is known as progressive error, which occurs when changes in responses are caused by the participant's experience in the experiment. For example, if the experiment takes a long time, they might get more bored or more hungry later in the experiment, and thus perform worse on measures that come up later in the experiment. The good news is that both carryover effects and progressive error can be minimized by either counterbalancing or by randomization. So, just to recap, there are 4 assumptions underlying the one sample and independent samples t-test. The first is that the dependent variable is on an interval or ratio scale. The second is that the dependent variable is normally distributed. The third is that the variance of both populations for an independent samples t-test are approximately equal. And fourth, that observations are independent. The dependent samples t-test reduces unsystematic variability by examining differences within participants between conditions. We calculate difference scores, x sub d, for each participant, in other words, condition 1 scores minus condition 2 scores. Then calculate the mean and the standard deviation of difference scores, and from this, calculate our test statistic. Using the logic of null hypothesis significance testing, we can estimate how likely a test statistic is to occur if the null hypothesis is true. And we reject the null if the test statistic is unlikely to occur under the null hypothesis.